Welcome to the first chemistry video on this channel. Today we'll be looking at AQA GCSE Chemistry 9-1 syllabus, Chapter 1 Atomic Structure, Chapter 1.1 Atoms. Okay, so let's get into the first part. Of this video. Let's look at some key points first. Okay, so number one, all the substances in the world are made up of atoms, okay? They're all made up of something called an atom, okay? So what is an atom, okay? An atom is what we call just a tiny particle. That's literally what we mean by an atom, okay? It's just a tiny particle, has a radius of approximately 0.1 nanometers, okay? 0.1 nanometers, and that is 10 to the power of minus 10 meters. Now, let's just look closely at what an atom is again, okay? So you might have seen something like this before, okay? This is a nice model of an atom, okay? It's a mildly accurate representation of an atom. We'll be looking at what the atom comprises of and what an atom actually looks like in future videos. But for now, for this video, you just need to be able to model an atom as this kind of spherical particle, just this tiny indivisible particle, something like this, okay? This is what we call an atom. It's a tiny particle and has a radius of approximately 0.1 nanometers. So what does that mean? That means the radius, the distance from the center of this particle to the edge, right? Center of this particle to the outer edge, okay? 0.1 nanometers. 0.1 nanometers. And that is just basically 10 to the power of minus 10 meters. If you don't know the actual the scale conversions of nanometers to meters, I highly recommend you go and look at that and familiarize yourself. It's very important, not just in chemistry, but in all sciences and math, definitely. So now let's go on to a new point. Well, if atoms make up all substances, right, then it raises another question, which is, why do we have different substances, right? Why do we have water? Why do we have, I don't know, aluminium? Why do we have sodium? We have all these different substances, right? Well, to explain that, we say that there are different types of atoms, okay? There are different types of atoms. And we'll look at this, what actually differentiates these atoms in future videos. But you can think about it like this, okay? You can think about it like this for now. These are some different types of atoms. Remember, they're not actually different colored atoms. That's not what sets them apart, okay? While substances that the atoms make up can be colored, atoms themselves are not colored at all, okay? It's just the different properties of the atoms which causes a particular substance to have a particular color, okay? So we have different types of atoms, let's say, and these atoms, basically, I would highly advise noting down all of this, by the way, but these atoms can be joined together in many proportions and combinations to form all the substances that we see around us, right? They can be joined together. And what I mean by joining together is that not like both of these are going to mix and form this new, I don't know, blue colored atom or brown colored atom, right? That's not what happens. They join, when I say they join, they literally, they physically join in a way that there's forces between them, okay? They're literally connected, and that causes them to form a different substance, and we'll see more about that even in this video and in the future as well. This is all going to make sense in the future. And some substances, we just said that these atoms can combine and in different proportions, but some substances called elements, it's a very, very key definition here, okay? Elements are made up of only one type of atom, only one. So an element, what is an element? An element is a substance that is made up of only one type of atom. Okay? One more important point is that there are approximately 100 known elements. It's a very key point that you need to know. The exact number is, I think, 118 that we found as of now. Some of them are radioactive, some of them are synthesized, but approximately 100. That's all you need to know in this course. Okay? And now I was talking about the aluminium block. Let's bring this in now. So aluminium is an element, right? And if we take this aluminium block here, if I were to zoom into this aluminium block, right? Let's say we zoom it with like a very strong magnifier. And what would we see? We would see atoms of aluminium atoms, all arranged in this nice fixed pattern. And what you would see is that each of these atoms are identical. Each of these atoms are identical to one another, okay? And that is because they are all aluminium atoms. If I were to take just one atom from here, Okay, that is an aluminium atom by itself. Okay, aluminium, just going to say Al for now. You'll see what that means later. But so therefore you can see that an atom is literally the smallest part of an element that can exist and be identified as that element. This last part is very important because if we were to take that atom, just look at it and look at its different properties, you would see that that is actually just an aluminium atom. If you look at that atom, look at its properties, look at what it comprises of, you'll see in the future that an atom is not just this spherical particle. There are actually things inside, protons, neutrons, and electrons. Inside you'll see electrons on this corner orbiting the nucleus. That's a very, very different concept that we'll look on in future videos. But if I was just to look at one of these atoms, I would know that it is aluminium, the element that we're referring to. So now let's move on to the next concept in this subchapter, which is about properties, literally just properties. And we have two types of properties, okay? Two types of main properties. We have chemical properties, right? And we have physical properties, okay? They're very different. You need to know the difference. You need to be able to describe different substances using these properties, okay? So what is a chemical property? Okay, what are chemical properties? Now let's look at that now. Okay, a chemical property basically just describes how a substance reacts, okay? It just describes how the substance reacts. That's the definition for you, okay? And let's look at an example of that. It would be, okay, reactivity in general, flammability, acidity. So let's take a substance, again, sodium, let's say. Say I had sodium, okay? It reacts with water, explosively with water, okay, vigorously with water. So that would be a property, that it reacts with water and other substances don't. It's something that sets it apart from many other elements, okay? Then you have flammability. It would be, in other words, how well a substance reacts with oxygen in the air, how it combusts, right? So you have many isotopes of carbon, maybe allotropes of carbon. They react with oxygen in the air. We see them burn in fossil fuel stations, right? That's a property of carbon, which is why we use it as a fossil fuel. We have acidity, different acids. You have hydrochloric acid. Hydrochloric acid is definitely an acid you've heard of, I think. May be different in its degree of acidity to something like sulfuric acid, right? So that is another reactive property, right? It refers to how the substance reacts. Okay, in this case, acidity would refer to how well a substance is an acid. In other words, how well it reacts with something like an alkali, let's say, or a base, right? We'll see much more of that in future chapters, okay, much more. Now, physical properties, okay, what do we mean by physical properties then? Characteristics of a substance that can be seen without changing the substance itself. This is the main definition, without changing the substance itself. Because when we're looking at reactivity, right, this substance is changing. The substance is changing because when it reacts, the substance changes in a chemical reaction. When sodium reacts with water, what is it? When sodium reacts with water, sodium plus water, let's say, right? It's going to form something called sodium hydroxide, which is a different substance, right? It's a compound, which we'll look at in the next slide, but it's one of the products of this reaction, and the substance has changed. Sodium has changed into sodium hydroxide, along with some elements from water, right? So you can't derive the physical properties of sodium from this reaction. You need to look at the physical properties, okay? For example, we'd have density, boiling points, and electrical conductivity. Density is just, mass per volume. I don't need to react sodium, for example, with anything. I just need to take sodium, I just need to take a sodium block on its own and observe the properties. So density was what? Mass per volume. Mass per volume. That's what we call density. Okay, you can think of it as how many atoms are there per unit of volume. how many atoms are packed together in a given space. That's a simple way of putting it. Boiling points, the temperature at which a liquid transitions, liquid goes into a gas basically. And for example, for water, you would have 100 degrees Celsius. That would be the boiling point of water. Okay. Take electrical conductivity. That is another key physical property. That I think that's self-explanatory, honestly. How well a substance conducts electricity. For example, many metals, they conduct very well. That's why we use them a lot, right? But other substances like, I don't know, many non-metals in general, they don't conduct electricity very well. So that's properties for you. So now let's look at the next set of points. So this is very important. Elements are represented by chemical symbols, and what they are the short 1 or 2 letter symbols that make it easier to universally recognize an element. And this universally recognized thing is a bit important, because if you think about it, different elements are called by using different names in different languages, but then for all scientists all over the world, or just anyone all over the world, to recognize an element, it can be achieved using this chemical symbol, right? So what is the periodic table? It's a table representation of the different elements arranged systematically. And this is one of the most important things in chemistry, is the periodic table. So let's show you that now. So this is the periodic table. You've probably seen it before. So as I said before, it's a table representation of the different elements arranged systematically. And each symbol represents the atom of a certain element. So this here is a representation of the hydrogen atom. This is lithium, beryllium, and it's just a periodic table of elements, and each of these element boxes represents an atom of that element. And we'll see why exactly this is an atom of this element and what it actually means in chapter 2, which is a full detailed chapter on the periodic table. But for now, just getting an idea of it. Okay, so the elements in each group. So now this is important. We'll come back to this point, but what are groups and periods? Okay, so this periodic table is bound to have periods and groups, which are rows and columns respectively. So we have all these groups. Okay, so the groups are the columns. So we have group 1, 2, 3, 4, 5, 6, 7, and we call this one 0. We don't call it 8. Again, in chapter 2 we'll see. We are going to disregard these as groups for now. Okay, we're just going to leave this. This is 1, 2, 3, 4, 5, 6, 7, and 0. Okay, and we call these groups, right? These are the groups. Okay, and then we have the periods, which are the rows. We have, again, 1, 2, 3, 4, 5, 6, and 7. Let's ignore these for now. Okay, let's ignore these completely. Okay, these are the lanthanides and the actinides, which is beyond your course for now. Okay, we just need to know about the groups and the periods. So let's just write a P for the periods. Okay, these are the periods we have, and these are the groups. Okay, so what does this one say? The elements in each group, okay, so the columns, have similar properties. Remember, chemical properties, physical properties, both. They're very similar, and they have patterns running through them. So let's take a group, for example. Let's take group 1, shall we? This is group 1 here. Notice that I've not included hydrogen in group 1 at all. H for hydrogen. We're not including it. I know it looks like it's in group 1, but sometimes in other periodic tables you will see it here, because it does not exhibit the properties of group 1. Okay, because group 1 are what we call the alkali metals. The alkali metals, and hydrogen is not a metal. It has fairly different properties. It's not gonna react like them. It's not, in most cases, not gonna react like them. It has different physical properties. So it's just there, but we disregard it when we're talking about the group 1 elements. Okay, so group 1 are the alkali metals. They have similar properties, okay, such as electrical conductivity. They're all actually pretty soft. Okay, electrical conductivity, EC for that one. Okay, many more properties. Again, there's a full subchapter on the alkali metals in chapter 2, I think, or chapter 3, chapter 2, I'm pretty sure. But we'll look at that in detail at some point, okay? So there's also a staircase line, okay, a staircase line, sometimes called the amphoteric line, but no, you just need to call it the staircase line, you just need to be aware of it. It looks something like this, you don't need to be able to draw its exact, structure, but this line divides the metals from the non-metals. So metals lie on the left of this line. So as you can see, most elements are metals. All over here are metals, right? All of these we have are metals, while this side is just the non-metals. The non-metals. Okay. And again, we'll look at differences between metal and non-metal properties, the main ones, in the future. Okay, so a few elements that are situated next to the line, like silicon. So we have silicon over here. Let's draw it in a different color. Silicon over here, right? Silicon. Okay, they're considered metalloids because they're next to the line. And what that means, metalloids, what that means is that they're elements that display both metallic properties and non-metallic properties. In some ways they behave like metals, and in some ways they behave like non-metals. They're somewhere in the middle, and that's why they're just right next to this line. So it's kind of going from metallic to non-metallic as we go here, okay? Metallic to non-metallic. Okay, I would really advise writing all these points down and really digesting the information, because the periodic table is a huge concept that we'll be using continuously throughout the entire course. So now let's move on to the next concept. So now coming on to compounds. I think I mentioned this about sodium hydroxide or something in the two previous slides, right? So what is a compound? A compound is a substance made up of two or more elements chemically bonded together. And this is very important, this concept, chemically bonded, not just mixed together or just put in the same bowl together. In fact, let's bring one bowl. Okay, so let's say we have this bowl, okay, and let's say I have, let's bring back aluminium, shall we? Aluminium powder, aluminium, this is the chemical symbol for it. Let's say we have aluminium powder, and let's say I also put in some magnesium powder, Mg, both metals, magnesium powder. I put in, it looks something like this, let's say. Okay, all these powders, but the powders are mixed, but they're just mixed. They're not chemically bonded together, okay? They're not a compound. There's something we call a mixture. Again, we'll come back to this in future videos, mixtures versus compounds. Okay, this is a mixture here, okay? It's not a compound. Because in a compound, you have to be chemically bonded together. And notice, a mixture is actually really easy to separate the powders back to just magnesium powder and to aluminium powder. But chemically bonding two elements together holds them together in such a way that they can only be separated by reaction. Only separated by reaction. You need a reaction to separate. Okay, let's just write that there. Reaction to separate the substances back into the two elements, or three. It's just two or more, remember? Okay, and what do I mean by chemically bonded? We'll come back to that, okay? So in the compound, the atoms of each element it composes of are in fixed proportions. So I think we need to take an example of a compound. Let's take a very common example. Let's take carbon dioxide. Definitely heard of carbon dioxide, I think. CO2 is the chemical formula. Come back to what that means, okay? Let's read through the points before we come back to carbon dioxide. So the atoms are all held together by chemical bonds, as it says they're chemically bonded together. The atoms of the atoms of all the elements, right? They're all held together by chemical bonds. Okay. Again, what these chemical bonds are just attractive forces. You can think of them attractive forces. Think of them as attractive forces. Okay, between the atoms. So a chemical formula is different from a chemical symbol, okay? Chemical symbol, we have, carbon dioxide. What does it contain? Carbon and oxygen, right? Carbon and oxygen. So C equals carbon, right? It's the symbol. O is just the symbol of oxygen as well. But this here is the formula because it tells us an expression for a substance made up of element symbols, C and O, and the relative proportions of these elements. Relative proportions. Symbols don't tell you any of that. They're just representations of an element, right? The relative proportions tells you about this compound. Look at this, the 2 over here. It tells you that for every carbon atom, okay, if we have 1 carbon atom, then I have 2 oxygen atoms. 2 oxygens. Okay, 2 oxygen atoms. It means how much ever carbon dioxide I take, 5 kilograms, 10 kilograms, the number of carbon atoms will always be 1/2 of the number of oxygen atoms. Okay, because the ratio is fixed. It's a fixed proportion, C to O2. Okay, the absence of a number here, I don't need to write 1 over here. Okay, I don't need to write 1. I just know that it's 1. If there's nothing there, it means it's 1. And let's come back to these chemical bonds. So if we looked at carbon dioxide, like I don't know, let's see this carbon atom like this, okay, and we have an oxygen atom here. Let's have another oxygen atom, and they're held together by chemical bonds. These chemical bonds are not actual rigid structures, but they're just a representation of the attractive forces, which are chemical bonds. Okay, attractive forces. So then I would have this molecule of carbon dioxide, many molecules like this floating around in the carbon dioxide gas. Okay, and one more thing, one key concept, many people get confused with this, again, between chemical formula and chemical symbols. Just because chemical formula doesn't have to be a compound, it can just be an element as well. Let's look at O2. O2, okay, O2, okay, is actually a chemical formula. It's not a chemical symbol because it's telling you relative proportions. Because in nature we find oxygen as a molecule. Okay, it looks something like this. Let's say we have 1 oxygen molecule, one oxygen atom chemically bonded to another oxygen atom, and that is a molecule floating around. Okay, this is the molecule. This is the molecule floating around in the air as part of this oxygen gas. This is a chemical formula. It's telling you the relative proportions. They're saying 2 oxygen atoms bonded together to make 1 molecule of O2. Okay, we find O3 as well in nature. We find O3, which is ozone. So just because we have oxygen doesn't make it a chemical formula. This is just a symbol. It's a representation of the element. In use, you need to make it into a chemical formula to show us what we actually mean, what type of substance we are referring to. So now, let's move on to more about compounds, right? So compounds, as you can see here, they're made during chemical reactions. So what happens in chemical reactions? At least one new substance, such as a compound, is produced. At least one new substance. I can't just take sodium and then let it stay there for 5 seconds and then say, oh, it's reacted to produce sodium. No. So sodium is just there. It doesn't react. Reaction means a new substance is produced. The final concept, I think, just the final one, the properties of a compound. The properties of a compound. It's a very important point, which is why it's written in huge here, very big. The properties of a compound are usually very different from the properties of the elements it is composed of. Okay, it's usually very different from the properties of the elements it is composed of. Let's take a common compound. You probably use it every day. NaCl. Let's write it nice and big here. NaCl. Do you remember the chemical symbols? This one here is sodium. Sodium, Na, chemical symbol, and Cl, chlorine. Okay, and as you can see, this is the chemical formula, so it shows that it's in the ratio 1 to 1, right? For every sodium atom, there's 1 chlorine atom. Okay, so in this compound, okay, you know what this is? This is sodium chloride. Sodium chloride, right? Let's just write the name here. Sodium chloride. This is sodium chloride. Okay, and it is table salt. It's the common salt we use at home. We use it in food and when we eat it, right? Okay, what are the properties? It's safe to eat. Safe to eat. Safe to eat. Dissolves in water. Wide variety of properties. But what about its constituent elements? Let's take sodium on its own, just sodium. Sodium as an element, okay, it's a metal, right? It reacts vigorously with water. Reacts with water vigorously. Okay, but when we have salt in our mouth, which has water, it doesn't explode, doesn't react explosively with water, right? With water. So as you can see already here, the properties of sodium are different from the properties of sodium chloride, because it's a completely different compound. It's a different compound. It's not an element. And just because it has sodium in it doesn't mean some of its properties are going to be like sodium. It's not. And let's take the other one as well, chlorine. Chlorine is, you don't eat it, it's a toxic gas. It's toxic and it's gaseous at room temperature, right? But sodium chloride is solid. Sodium chloride is solid at room temperature. So clearly, as you can see, the properties of the elements, okay, are very different from the properties of the compound. So you can never just infer the properties of a compound from its elements, because usually the properties of the compound are completely different from the elements. The properties of the elements doesn't influence the properties of the compound whatsoever. It's very different. It all comes down to the bonding of the substance, which means what type of attractive forces do we have between the sodium atom and chlorine atom. And we're going to look at that in the future of this course.